Buonasera. Buonasera e benvenuto all'Accademia Americana a Roma. I am the president, Peter Miller, and I am especially happy to be standing here introducing this event. For tonight, we mark the 413th anniversary of Galileo Galilei's coming to the home of the American Academy, just a few meters away from where we sit now, to demonstrate what we call the telescope, named on that night, for the first time in Rome. A historic occasion which, looking back from here, may seem the dawn of a new age. I want to begin by thanking those who made tonight's lecture possible, for support, the Arete Foundation in Philadelphia, for organization here at the American Academy in Rome, Ann Coulson, Tina Cancemi, and of course the director, Dr. Eliza Wang, and for the website, Andrew Mitchell. But we are tonight not only marking a significant moment in the past, but also one in the present. For with the inauguration of the Galileo Night Lecture, we hope to inaugurate a new relationship between the sciences, arts, and humanities at the American Academy in Rome. Building on the series of lectures in the early 2000s, sponsored by Cynthia Polsky and Leon Hazen, we are declaring the fundamental unity of human creativity and also the great value for each of this conversation between sciences, arts, and humanities. In this, we can, of course, be inspired by Galileo himself, who was a mathematician, who did experiments, but who also presented his research in the form of literary dialogues, who wrote a book about contemporary poetry, and whose father developed the modern genre of opera out of the conversations he had with his friends of many different intellectual disciplines in Florence in the late 16th century. For this launching of the Academy back to the future, we could hardly have a better guide than David Spergel, president of the Simons Foundation and Charles Young Professor of Astronomy Emeritus at Princeton University. Using the cosmic microwave background radiation, he has studied the age, shape, and composition of the universe. As co-chair of the W1st science team, he is directing a project that will study the nature of dark energy, complete the survey of extrasolar planets, characterize the atmospheres of nearby planets, and survey the universe with more than 100 times the field of view of the Hubble Space Telescope. Last year, he chaired NASA's Committee on UFOs, not its real name. Its real name was, I kid you not, Independent Study on Unidentified Anomalous Phenomena. And on Google, he has been forever immortalized for his internal memorandum, Thoughts on UFOs. His 2001 MacArthur Fellowship has been long since submerged under a weight of subsequent prizes, including the Shaw Prize in Astronomy 2010, NASA Exceptional Public Service Award 2017, and Breakthrough Prize in Fundamental Physics 2018. Our commentator tonight is Sauro Succi, senior researcher at the Istituto Italiano di Tecnologia at La Sapienza in Rome, where he is PI on the project Multiscale and Quantum Simulations. He is also professor in the School of Engineering and Applied Sciences at Harvard University. From 1995 to 2018, he was research director at the Istituto Applicazioni Calcolo of the Centro Nazionale di Ricerca. He is internationally credited for being one of the founders of the successful Lattice-Boltzmann method for fluid dynamics and soft matter. And in 2024, he was co-recipient of the Aspen Institute Italia Prize. Most recently, he is author of Sailing the Ocean of Complexity, Lessons from the Physics-Biology Frontier, Oxford 2022. The title of tonight's talk is Physics as Aesthetics, Cosmology as a Historical Science, From Galileo to the Big Bang. Let me conclude my remarks tonight by pointing out that this issue Spergel addresses of the relationship between experiment and history is no mere bagatelle. In his most recent book, the Italian historian Carlo Ginzburg makes 2 points worth considering tonight. The first is that history, as an observational rather than an experimental science, is much closer to geology and astrophysics than to other sciences. The second is that, nevertheless, in testing her evidence, the historian comes much closer to experimentation than we might generally think. For Ginsburg and his classic analogy, the historian in this is like the judge, for whom a trial is a kind of historiographic experiment. Nor was this focus on experiment Ginsburg's innovation alone, for he sends us back to Marc Bloch and his testamentary Métier d'un historien, or historian's craft, written in hiding in 1943. It is Bloch who describes the relationship of the historian to evidence as that of, and I quote, a physicist who, confined to his bed with a cold, hears the results of his experiments only through the reports of his laboratory technician, close quotes. Bloch refers to historical sources as, and I quote, the subjects of my experiments, and who nevertheless argues that, and I quote, the experiment leaves behind certain residues which the historian can see with his own eyes. Finally, Bloch describes the cumulative work of history upon the reshaping of our collective self-understanding as the result of, again I quote, the patient labor of an experiment performed upon man himself as a witness. Bloch gives as an example of this kind of work the study of a Roman funerary inscription of the sort we might imagine that line the walls of the cortile just above where we are now sitting and which we will walk past later. It looks simple, and yet, he writes, nothing could be more variegated than the evidences which there await the probing of the scholar's lancet. Lancet is the giveaway word. I won't take you through Bloch's marvelous teasing out of all the questions to be asked from out of that simple stone. It's in chapter 4, if any of you want to go back to it later. But just go straight to his conclusion. I quote, a notebook of experiments is not to be confused with the moment-by-moment diary of everything that has happened in the laboratory. And so, under the auspices of Galileo, whom I happily claim tonight as the first, if necessarily only honorary fellow of the American Academy in Rome, it is my pleasure to invite a physicist, David Spergel, to this podium and into a conversation launched for us already by two of the greatest historians of the 20th century. Thank you.
Thank you, Peter. It's a great pleasure to be here. It's a real great honor to stand really on the grounds where Galileo certainly began what I think of as modern astronomy, and a place that really helped, a moment that really shaped modern science. And it's an opportunity to think about our craft as scientists and how it relates to the act of the historian, the act of the artist, what drives the way we do what we do and think about what we do. I want to do that by looking at my own field, cosmology, and tell the story of how our ideas have evolved and how we approach it, and I would say arguably like historians. We look back. For us, what we observe is our archive, and a very incomplete one, and we construct our understanding from that archive, driven by our aesthetic sense, in some ways, of what is elegance and what is beauty. So I want to begin, in a sense, with my conclusion, which is, what is our understanding of the universe today? And our understanding is a universe that is, on one hand, remarkably simple. I can describe all the basic properties of the universe we observe out beyond us in terms of 5 numbers: the age of the universe, the density of atoms in the universe, the amount of dark matter in the universe, how lumpy it is, and how that lumpiness varies with scale. And I'll go through some of the things we observe, and in the end, the conclusion is, this is all we need, together with the physics that we see on Earth, to describe what we see out there. And that that's a remarkably simple and, to me, very surprising result that we've learned in the past couple decades. And while it's simple, it's also strange. Atoms, the stuff that makes up us, makes up only 5% of the universe. It's a moment of kind of humility to have to say, we don't know what makes up 95% of the universe. We know that most of the mass in our own galaxy, the Milky Way, and in other galaxies, is made of dark matter. We know that there is energy associated with empty space. We don't know why it's there. We don't understand its amplitude. We have, I would argue, almost no theoretical understanding of what we see, yet it's most of the universe. We know that the universe started out lumpy. We know that the universe, we don't know how it got there. We know we expect the universe to be symmetric. There exists both matter and antimatter. In some ways, antimatter behaves as matter, in a sense, reflected in a mirror. Yet there's a broken symmetry somewhere in nature. We have ideas, but there's nothing proven or really that because of that, we have more protons than antiprotons. We think in the early universe there were 1 billion antiprotons, say, and about 1,000,000,001 protons. There's just this tiny excess of matter over antimatter that enabled our existence. Otherwise, everything would annihilate. We don't know where that comes from. We don't know what drove the early expansion of the universe that led to the fluctuations. And we don't know, we have a model, the Big Bang model, that posits the universe began 13.8 billion years ago. But we don't know what drove that expansion, what was before then. We have this model that on one hand is both very simple, very elegant, but filled with big open questions. And to give you, and that's my conclusion, right, was that where we're going to end up, and I'll tell you how we got there. And as we go along that path, I want to talk about this notion that Peter brought up as cosmologists, we really are historians. We do not do experiment. We certainly do not generate the Big Bang. We can't vary the conditions. We look out in space and we see what's there. The advantage we have, I would say, over other areas of history, is that physics is simple and much simpler than people. And we can rely on aesthetics and extrapolation from laboratory physics as a guide as we build our model of the past. And now let me sort of talk about special relativity, which is what makes us, in a sense, historians. Life travels at a finite speed. You see me not as I am, but as I was a few billionths of a second ago. You look out at the sun, you see the sun as it was about 8 minutes ago. It takes light about 8 minutes to get from the sun to here. If you've seen the movie The Martian, you may remember the scene in which it takes about 30 minutes for a message to get to Mars, and then for the abandoned astronaut to get back to the people on Earth, and then that you have this delayed conversation. Those of you my age, even somewhat younger, may remember what phone calls were like from Rome to New York, right, where there was that pause, and it actually took a second or so for the signal to get through back and forth. And you would not hear the conversation smoothly the way we do today, but with this delay. And that's what it's like, more dramatically, with Mars. The further out you go in space, the further back you go in time. When we talk about a nearby star being 10 light years away, or say 50 light years away, which is sort of typical for the bright stars you see in the night sky, you're seeing them not as they are now, but as they were 50 years ago, was it took light 50 years to get here. You see the Andromeda galaxy as it was about 1 million years ago. And people on Andromeda, in the Andromeda galaxy, are observing us as we were 1 million years ago. So you're seeing the past. And let's take the Andromeda galaxy, which is the nearest big galaxy to us. We see it as a certain orientation. We don't get to choose that orientation. We see that projection. What we see is obscured by dust. What we see is an incomplete projection. In the case of Andromeda, it's close enough that we actually know the angle. But most of the time when we look out at distant galaxies, and I better be careful, I'm pushing this down, so I better keep raising this up and balance. We see distant galaxies at very different orientations and at very different times. And we only see any individual galaxy once, right? We're not, the one we see that is 1 billion light years away, that we see with the Hubble telescope, we see a different galaxy 10 billion light years away, 10 billion years ago, with the James Webb telescope. And we are trying to construct a complete story of how galaxies evolve without following an individual. You're just seeing moments in their history, and you're seeing them in ways in which, we have no control over what we observe. And I think in some of our observations, I think we are often perhaps like what I understand what it's like to be a classicist, where what you see is what happens to get to you. You don't, you would love to have all the certain documents. Well, it wasn't, you don't get to choose. It's what, in our case, the universe hands us in terms of what we can see and what we can observe. For us, of course, the most frustrating thing is since we don't know what most of the universe is, we observe the effects of things like dark matter only very indirectly because it curves space. And that means light follows this path of deflection. And by how light is deflected and how images are distorted is the only is our most direct way of actually inferring the distribution of dark matter. So, we are very much shaped by our observations. Right? So that's sort of, and, but I think what makes our job easier is that mathematics, for reasons we don't understand, turns out to be the language of the universe. And this is from Galileo: the universe cannot be read until we've learned the language, become familiar with the characters it's written in. It's written in the mathematical language, and the letters are triangles, circles, and other geometric figures, without which means it is humanly impossible to comprehend a single world. A more modern version of this is given by Eugene Vigner, who was my colleague when I first came to Princeton. He talks about the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wondrous gift that we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in the future and that will extend, for better or for worse, to our pleasure, even perhaps to our bafflement, to wide branches of learning. And this is what I meant by physics as aesthetic. Because we have a sense of what is elegant in mathematics. We use that to develop our ideas. And it works for reasons we don't understand often. And as I'll demonstrate in the talk, sometimes it leads us astray. Sometimes we think the universe ought to be elegant in a certain way. Atoms should be all there is, for example. And the universe doesn't live up to our expectations. It chooses a different way to be elegant. Now we've gone, started with special relativity. Now let's turn to general relativity. And this very much was a theory that Einstein built on his aesthetic principles, with the goal of replacing action at a distance with geometry. And this notion of that gravity acts at a distance, Galileo was disturbed by. Galileo was exploring this, and it's how Galileo and then Newton developed their ideas. I think he would have loved general relativity, actually, from what I've read of Galileo's work. The key idea in general relativity, or two key ideas, is matter tells space how to curve, and the curvature of space tells matter and light how to move. And this is demonstrated by what happens during an eclipse. Those of us in the United States just experienced one as an eclipse that passed from Texas to Maine. I had the good fortune of being in Austin last weekend to see that eclipse. And when the sun passes in front of a distant star, a star that was at position A, its light gets deflected and it appears at position B. And in 1919, Eddington led the great eclipse expedition that tested Einstein's theories. And there we are in the New York Times in 1919, where, discussing the triumph of Einstein's theory. I like the idea of people being more or less agog. I think today we would try to avoid saying men of science, but this was the world of 1919. To me, the thing that they missed most was this phrase, actually. The stars were exactly where Einstein said they should be, and that was the great triumph. Now, these observations, which are the basis of general relativity, are very much observations, right? Einstein couldn't do this experiment. You had to wait for an eclipse where the moon was just at the right position and recognize that nature would do an experiment for us. And that's what we get to observe, right? And this is really what we do as astrophysicists. We rely on what nature offers us for experiment. So once we have general relativity, it leads next to the expanding universe, or in our modern version. And this is, I think, conceptually the most difficult idea, because most of us have a Newtonian or Galilean, actually, notion of space and time. We think of space as having to structure. General relativity tells us the whole universe is expanding. The distances between galaxies are growing with time. And this leads to a couple different, I think, wrong pictures. People ask, what is it expanding into? I think the best answer is the future. That these, to take a sphere like this, this is how I think of the universe, not that we'll get to this particular thing in a moment, but as a sphere, and we're on the surface of a sphere, and the radius of the sphere is time. And this is a two-dimensional sphere. Really, you want a three-dimensional sphere in force space. That's harder to visualize. But just imagine different galaxies are ants on the surface of the sphere. And that sphere is growing and expanding. And the radius of the sphere is time. So as the universe gets older, it gets bigger and bigger. Now let's run time backwards. It gets smaller and smaller. Eventually, this sphere, if I were to deflate it, would collapse down to a point. And you'll notice every place on the sphere collapses to the same point. So the Big Bang does not happen at a place in space. It's not like the Big Bang happened over there. It happened everywhere, but it happened at a moment in time. And that's our current understanding. Einstein actually made a couple mistakes in developing this theory. And they were mistakes driven by his aesthetic. he understood the theory predicted that the universe was expanding or contracting, and that the universe would have a beginning in time. And he thought this was an awful prediction of the theory. He thought that there was, as far as he knew, there was no evidence for expansion, and he modified his theory by adding an additional term to the mathematics that made the universe static. And this was his greatest blunder. He actually could have predicted from his theory the expansion. He knew that was there. But the notion of a universe that had a beginning went against his sense of beauty. And in fact, I have a number of colleagues who don't like our current understanding on this aesthetic ground. And this is something that I think has guided us in physics a lot, is a sense of symmetry and beauty. And it has often led us to new insights, but sometimes led us astray. And this is, even Einstein was led astray. And it was Edwin Hubble who first measured the expansion, and this shows a plot of the brightness of galaxies versus how fast they move away from us. And I think I did not reproduce the axes. I would get a poor grade if I handed this in my own classes. But you just see a plot of distance versus brightness, and you can see that the current data is quite good. The further away a galaxy is, the faster it moves away from us, and this was the evidence of the expanding universe seen over 100 years ago, the first data. First papers weren't published to 29. Actually, my one experience in the archive at Princeton was looking at Henry Norris Russell's papers and finding letters from Hubble coming from California to the West Coast saying how he looks forward to staying at Russell's home, seeing Henry Norris Russell and his wife, and describing some of his new work. And then there's a letter back in which Russell writes and asks for permission to show in his 1927 textbook, before it was published, Hubble's new data, and it's there in the 27 textbook. I know this because, again, I think this was one moment I had the pleasures, I think, that many historians have had somewhere. And I found myself in a bookstore in Britain, in a little town just south of Edinburgh, and I found a copy of Russell's 1927 textbook on sale for £6, which I bought instantly, and found Russell's descriptions of that. And that's actually what drove me to the archive to look for how did Russell get this result before Hubble published his 29 paper? They'd come to visit and showed him his data. Okay, so now let's talk about this model we have today. It's basic assumptions, initially assumptions that were driven by aesthetic, that the universe is uniform and isotropic on all scales, that the laws of physics are the same everywhere and don't change in time. And when they posited these, they really had no evidence for them. This is our current picture of the universe. It starts out very hot and dense. As it evolves, it cools. During the first few minutes, the light elements, helium and deuterium, form. After about 400,000 years, the first atoms form. About 100 million years later, stars form. After 1 billion years, galaxies form. And what we do with telescopes like the James Webb Telescope is we aim to look back to 500 million years after the Big Bang and seeing the earlier galaxies. What I'll talk about in the rest of my talk is our observations of the microwave background, the leftover heat from the Big Bang, and that lets us look back 13.8 billion years to roughly 400,000 years after when atoms first formed. So this shows an image of us looking out in space, looking back in time to the moment when the universe made its transition from ionized gas to neutral atoms. Actually, I'm going to skip this and talk about, well, actually, maybe I will say just quickly. Just want to give people a sense, again, of like aesthetic driving us in the wrong direction sometimes, but I think that's, we always tell the story of success. What I worked on as a young faculty member was the idea that when water freezes, it goes from one state to another. It's something we call a phase transition. When phase transitions happen, you form defects in the crystal. Those are ice bubbles. Those little air bubbles you see in ice cubes, those are defects because the crystal is imperfect. There's energy associated with those defects. And we explored the idea that the universe underwent phase transitions like that as it went from having only one type of matter to many types, as it went from the forces of nature being unified to not. We know that it underwent these phase transitions, and we thought that there might be energy associated with these effects, and they would drive structure. And what happened was, back in 1990, there were the first observations of the microwave background, and they showed the amplitude of fluctuations. And they showed an amplitude that was about a factor 2 below, maybe almost 3 below, what we predicted. So my first quote in the press is saying, "We are dead," as we looked at the observations and realized they didn't fit what we had hoped to see. And so sometimes we're led astray. The model that we do have as our best model is one that we call an inflationary universe model. It's also associated with the idea of a phase transition. But in it, the universe goes through a stage that we call a false vacuum. And that's something like supercooled water. If you go into a steam bath and you walk in and the water just condenses on your body, right? That's because it's been in a supercooled state. And there's energy associated with that. We think the universe was in this supercooled state. The energy associated with it drove the universe to grow exponentially. It took a very small patch, drove it, and made it very large and nearly flat geometry. And this model predicts a nearly flat universe with scale invariant fluctuations. So let me say a little bit about geometry and destiny. This is something I think Galileo would have loved. General relativity says that the density of matter determines its geometry. If the universe's density is high, then space is positively curved. The sum of the angles of a triangle are greater than 180 degrees. It's like we're living in a universe that looks like a 3D version of the surface of the Earth. The density is very low. The sum of the angles in a triangle is less than 180 degrees. It's hyperbolic space. And if it's flat, density is just right, that the energy in expansion is equal to the energy by gravity. The geometry we learned in high school or middle school, that the sum of the angles in a triangle is 180 degrees, is valid on the size of the universe. And geometry is destiny. The universe is positively curved. There's enough energy for it to collapse in a big crunch. If it's negatively curved, it will expand forever. Alan Sandage, the leader of the Harvard Observatory, explained this to Robert Frost at the faculty club, which led to the poem, "Some say the world will end in fire, others say in ice." And its fate depends upon the geometry of the universe. And our goal in this field has been to really follow Galileo's advice, which is measure what is measurable and make measurable what is not so. And what we've been able to do is measure things like the geometry and shape of the universe by looking at observations of the microwave background. So how do we do this? We look out in space and we look at fluctuations generated from the very early universe. And those fluctuations are generated by sound waves. And I can do an experiment to show you how that works. I'll create a region of high pressure, generates a sound wave. Sound wave moves out. The distance the sound wave moves, and 300,000 years in the early universe, is about set to be about 300,000 light years. So nature holds up a ruler to us, and we observe the size of those fluctuations. And depending on this length is the same, depending on the geometry of the universe, that determines the pattern of hot and cold spots. And that's what drove us to build an experiment to look for this, and this is work initiated by my late colleague David Wilkinson when he passed away from cancer soon after we started our analysis, and NASA generously let us name it after him, the WMAP mission. And what we did was we went out, we made this map, right? And that's a map of the universe looking out in all directions. And this is the pattern of fluctuations that we see from the Big Bang. And you can look at the size of hot and cold spots here. And this is a map. We do it at different frequencies. This is our lowest frequency. And this big red thing, which is what your eyes notice, is our own galaxy, the Milky Way. That's gas and dust in the Milky Way, right? And you're looking out at some distant horizon, and this is the stuff in the foreground. And as you change frequencies, it gets dimmer and dimmer and dimmer. And then you can combine the frequencies to make the baby picture. And I put up a picture of Stephen Hawking because during his talk on this, my colleague and I noticed the letters SH appear in the map. And this does not represent, I think, a message about this, or at the time I claimed it was also Saddam Hussein's initials. And let's not take that message. You know, but it shows our ability to find patterns, even when they're not there. And what are we seeing physically there? Those are the sound waves moving out. This spot in the center, this cold spot, is dark matter that doesn't move. The ring that moves out is a sound wave in electrons and photons. What we're doing in terms of our measurements is we look at the amplitude of the cold spot, the amplitude of the hot ring. The ratio of the two gives us the ratio of atoms to dark matter. That's one of those fundamental numbers. The width of the ring gives us the density of atoms because it tells us how the ring spreads. The size of the ring in projection gives us the geometry. And the amplitude of overall the signal gives us the lumpiness of the universe. That's our analysis, and that's all it takes to describe the universe, which to me is just incredibly simple. And we actually see a combination of these waves. So we could do them and look at this in a number of ways. I think the simplest way to think about our analysis is we take that map, we take the hot spots, we stack around every hot spot what the map looks like, add it up. You get that pattern of a ring around a hot spot, a cold ring around a hot spot, a hot ring around a cold spot. And we see the same pattern not only in the microwave sky, but in the large-scale distribution of galaxies. This is how we actually analyze our data, doing something we call harmonic analysis, where we look at the amplitude as a function of scale. And this shows the amplitude versus scale. These are data points from different experiments. This is, and this shows how we fit these things with only 5 numbers. Let me go, and what I think you should take away from this is we have a simple theory, a handful of parameters, and we fit it all with these 5 numbers, and we get different measurements from different experiments, and they give us a coherent picture. And to go back to my early theme, I think this is something where, in one hand, this looks like, science as we were taught, in junior high school. that you have a theory and you do experiment, you make measurements and so on, and the theory fits the data or it doesn't. Well, of course, that's not what's going on. We didn't design this experiment. Nature did this experiment. We get to observe it. We construct a theory, and the theory could have been so much more complicated. We use our aesthetic to design that theory. And the shocking thing is simplicity works, sort of, in that we've got this dark matter, we've got this dark energy, we don't know why there's actually most atoms. You know, there's things we don't get, but in some ways it's very simple. And the fluctuations are what we call Gaussian. There are equal number of hot and cold spots. It's about as simple as you can get in terms of its distribution. It follows a bell curve distribution, which has no parameters. And we can take what we see and do computer simulations of how galaxies form. So we take that universe we see a long time ago, we predict what we should see in the galaxy distribution, and it matches the statistical properties of the galaxy distribution. It looks like that. The large-scale galaxy distribution looks roughly like this. Not in this exact realization, because we're seeing different times, but in terms of their clustering properties. And we study this with big galaxy surveys, and there was just some recent results that came out on this. It's something we continue to improve. Results came out last week that generated some excitement. And our microwave background observations continue to improve. I mentioned the COBE results early on that showed my own theoretical ideas failed. Our work with WMAP, and then a decade ago, the European Space Agency and folks here in Rome played a significant role in building some of the detectors for it, measured with even higher precision with the Planck experiment. And you can see, you know, how things improve for us. You know, in the spirit of Galileo, our telescopes keep getting better, so we can observe more and more. And this shows how the Planck measurements, how you really can now zoom in on a scale much finer than the figure I showed to see more details. And here are the Planck maps now at 9 frequencies. So, and here's that same plot, in a sense, slightly different, where we're looking at data from 9 years of data from WMAP and the Planck data from, this case, from the first 2 years. And this is now a decade ago, and data we took from the ground from Chile, in the Atacama, and data our colleagues took from the South Pole. And you see, first, that the data is all consistent in terms of its properties. Funny symbols on the axes, but it's amplitude versus scale. How lumpy the picture is as a function of scale, and that's just the units we use. And we continue to improve. I mentioned we make measurements in Chile. Here's pictures of our telescope being constructed in Chile. The telescope about 2 years ago started to really fall apart. So this is being constructed. I've got one of those plates in my bedroom. So it's now fallen apart. And we took all the pieces apart and shared them among all of us. You know, we've gone from, here's the measurements that Planck took, which was a big improvement on what we took, which was an improvement on what COBE took. And there's improving things more for the measurements from the ground. This is data from 2016. We've done many more observations. I now have maps that are much higher precision, but we're not allowed to show them yet. The way these collaborations work, we have a big public announcement. So I have seen the maps. We will release them within about 3 or 4 months. We are doing something called blinding, which is we do not look at our own data in any way until we freeze our analysis, because we don't want to be prejudiced by our conceptions on what the results should look like. So we wait until we have done all the checks on the data, and checking only ways in which it doesn't reveal the results. So we look at the data measured on Monday and Tuesday, take the difference between them, and that should be 0, up to noise, and test our noise theory. We don't add the data together. So we're in the process of doing that. So let me conclude. I hope I gave you a taste of what we do in cosmology. And it's a sense that what we do, on one hand, seems very precise in terms of these models. Fundamentally, we're historians trying to reconstruct the story of the past based on incomplete observations. And we can go do this by kind of filling in the holes in what we don't understand, really on aesthetic principles driven by what seems mathematically elegant to us, or maybe seen by what we can actually solve in terms of the equations. So, Einstein assumes the universe is uniform because that's the only solution he knows how to write down the equations for. Then it turns out he's right. And this has somewhat been the story of what happens, right? Galileo observes the motion of the planets with high precision, building on work by Kepler and Brahe. And the laws that he helps derive, which then lead to Newton's work, are remarkably simple. The laws of gravity would not have to be the same for Mars and Jupiter and Saturn and distant stars, yet it all seems to work. And this way in which we work, particularly in cosmology, where we simply, we don't get to create universes, makes us, I feel, in many ways, kind of more akin in how we need to be thinking, and also how we need to remind ourselves of how we're thinking with historians, where we have to recognize the incompleteness of the record we see, and to recognize as physicists, we are often driven by our sense of beauty. And that has turned out to be a powerful guide in our understanding. So I hope you've enjoyed that initial tour and thoughts. So thank you.
Should I just go? Okay, so good evening, everyone. I'm really, truly honored to be and humbled to be here today in this magnificent venue. And talking after David is, of course, a very tall order, but I'll do my best, And I'll try to pick up essentially on the aesthetic part, much less on the history part, maybe next time. So, and in fact, what I'm going to, the idea I would like to push forward is that the development in modern science somehow suggests that we should revisit the way we think of aesthetics in physics. And just since we are among artists, I appeal to kids, and as you will see, the point is that we should go beyond the picture that John Keats gave of beauty and truth. So, speaking of Galileo, as you know, besides gazing at stars, incidentally, he is also the founder of the scientific method. Scientific method which I represent here as a triangle, theory, experiment, and simulation, because I have to advertise my own activity, computer simulation. But the idea of the scientific method is that in the end, the real channel between truth, meaning real life, is for experiment. And that was the big, new paradigm in science. Now, if you go to theory, the typical words you find is, and David mentioned simplicity, sort of, mathematical elegance, symmetry, invariance, so on and so forth. They all speak one word, which is beauty, okay? But what does beauty mean, in fact? Before I go into that, let me remind that this idea of being inspired by beauty has worked wonders all across, from the very tiny, particles, quarks, and even below, all the way up to cosmos. And you know this gentleman, right? I'm very jealous, David, as you know. You cannot compete with the fascination of cosmology, so I don't even try. Yet there is fascination, and there is a lot, actually, of complexity around what I call the anthropocentric dimension, namely, in a very generalized sense, the dimension that we can see, things which are somehow around 1 meter, maybe down to the nanometer, the cell. And the claim is that that's where complexity tops, okay? So we make this claim, David, for the complexity is not, you don't find the top complexity neither in the very, very small, neither, I'm sorry and apologize, on the very large scales. Okay, kids. Kids, and I'm not certainly here to teach you about kids, but as a famous statement back in 18-something, truth is beauty and beauty is truth, right? Beauty is truth and truth is beauty. And as a scientist, honestly, you say, okay, so what? Nice saying, but what does it really mean for me? Actually, as David has pointed out, that has been spectacularly successful in physics. But spectacularly means spectacularly. So David mentioned Einstein. Here comes another big man in science, is Paul Adrien Maurice Dirac, who in the 30s just predicted, before it was observed, antimatter, okay? And based purely on aesthetic consideration. It was just driven by the idea of merging quantum physics, which was just born, and relativity. And out of this, he just cooked up this famous equation, which predicted antimatter, which was found just a couple of years later. Read Dirac, a theory, I don't wear my glasses, with mathematical beauty is more likely to be correct than an ugly one that fits the data. That speaks, but there is a flip side of the very same medal, which is, in my view, I just discovered that during preparing this lecture, the negative side, which conveys the same message. Thomas Huxley said the great tragedy of science is the slaying of a beautiful hypothesis by the sheer mingled ugly. This is even stronger in a way, right? So, and as David also was mentioning, now there is a little itch with theoretical physics, particle physics, not theoretical physics, that this idea of going after beauty works until it does not work anymore. And in elementary particle physics, actually there is a problem like that. People have gone through a spiral of abstraction, beautiful math, but the answer of Mother Nature has been consistently no, no, no. So this is a book far too aggressive to my taste, sorry, by Sabine Ossenfelder, but she has a point. Says, isn't it that maybe we are going too much for this beauty? And David has already given in that you should go for beauty up to a point. I think there is a serious question here, and mostly for the artist, but for the scientist as well. Could it be that beyond a certain level of complexity, we have to accept or speculate that nature starts to accept, or maybe even like, some form of ugliness? What is ugliness? I leave it for you for now. I don't know. But let's go after this speculation. And ugliness, I'm mentioning complexity. That's a keyword. Again, Stephen Hawking, he was not a scientist of complexity, but he predicted that this century would be the century of complexity, besides, of course, cosmology and astrophysics. Complexity is usually associated with humans, and particularly the human brain. This is Ramon de Cajal, and this is supposed to represent a neuron. I mean, he likes to draw, this is a drawing, but it conveys the idea of complexity, and the neuron, he was the one, in fact, identifying neurons as the units of functioning units of our brain. What is a complex system? If it is not simple to say by definition, but let me pick up just one fact. You have to combine your universal principles, symmetry, elegance, etc., which govern our world as we know it, for sure, but there are ugly details, dirty details that we have somehow to take into account. And I think David agrees that as a theoretical physicist, you are trained to sweep the ugly detail under the carpet because they don't matter, right? Well, you come to a point where they do matter. Let me give you a few examples. Order disorder is another way of, disorder would be the ugly guy, and order would be the platonic beauty, but they have to somehow mesh together. And I cannot resist, we are in Rome, finally Giorgio Parisi brought the Nobel Prize back, and the Laudatio was done by this other gentleman, whom I know very well, John Bettlaufer. He was in the Nobel Committee, and this statement surely comes from John, is beautiful. discovery of interplay of order and disorder, beauty, my wife tells me that I'm not Earth anymore, and fluctuation in physical system from atoms all the way to planetary. Remember my very first slide, okay? Now, let me give you two examples of details which sometimes are not ugly at all. This is a calculation we did a few years ago, and I'm pretty proud, actually, to say that just 2 weeks ago we were told that we were awarded the Aspen Institute Italian Prize for US and Italy collaboration. We are very proud of that. Here goes the story. This is a beautiful living animal called Euplectella. It's a sponge. And the sponge managed to live at minus 500 meters out down in the Pacific. It is very beautiful. Actually, in Japan, it is offered as a wedding gift. Why? I don't know whether you can spot the shrimp. I can't because I forgot my glasses. But it's called forever together in Japanese because the shrimp is so happy there that he never quits. So in America, you say, I'm happy as a clam. Here you should say, I'm as happy as a shrimp, right? And so, but in fact, people have studied how does this living creature manage to live down in the abyss. But from the structural point of view, if you blow up this picture, you will discover fantastic structures in this living. It's silicon, basically, it's glass. So we do fluids, we run a very huge computer simulation, and this is an example of patterns of the fluid, and much to our delight and surprise, we discovered that this pattern, where there is no symmetry, but there is beauty, I would say. I hope you agree that there is some beauty without symmetry here. This pattern not only serves mechanical functions, but also serves feeding purposes and sexual reproduction. And that was totally unexpected. So just to say that here is a typical case where the details of the structure, which are not ugly at all, they're beautiful, they shape up the fluid motion. And so there is a synergy between structure and fluids, fluid and structure. And out of this synergy, possibly, you have a pattern for survival of life in the abyss, which is interesting, in my view. Second example, again, from my own work, some details, I don't know whether they are ugly or beautiful, but they're scary. This is, would you guess what this is? This is a protein which is basically managing the traffic of, is a neuroreceptor, and you have neurotransmitters which are supposed to flow from the outside of the cell to the inside through this channel. But this channel is not a pipe. This channel is breathing, okay? And I find it beautiful and scary that a defect on this breathing detail, dirty details, scary details, ugly details, you name them, a defect on the scale of 1/10 of a nanometer, so 1 billion times more than we are, and again a factor 10 below, can change the way you perceive the world. These defects are basically lay at the ground of neural diseases or depression. And we know very little about this. I find it scary that who you are may depend on a breathing defect of this protein. And again, not that the protein would violate any of the universal principle. You cannot, the universal principle gives you the fence, but inside the fence there is a lot of freedom, and that's where the detail matters. Okay, so now I'm getting far-fetched. You will forgive me, but we are supposed to initiate a dialogue between scientists and artists. I think, and I really mean it, that the science of complexity can really serve as a bridge, a serious bridge. I'm talking serious science and serious art, between art and science. And you know, this fantastic object is just a few minutes away from here, right? So I couldn't help but showing Michelangelo. David mentioned that the universe can be described in 5 numbers, but he also added very wisely, sort of simplicity. There are some, this is the kind of thing which goes beyond the sort of, and he knows much better than I do. This is a neutron star which is spiraling around. It's just a dance between a neutron star and a black hole. And I promise, because I took a look myself, I'm not a professional astrophysicist, but I'm curious, so I studied a little bit this system, and I promise that there are a lot of dirty details, right? Dirt is always quote unquote. And I cannot help but bringing up a visual analogy to you. And the analogy, so this is cosmological complexity, the sort of that mentioned, the David mentioned. And look here, there is another stargazer, and these people do not need, any label. Vincent van Gogh, who said, I dream of painting and I paint what I dream, right? But to me, the analogy, and it might be a serious analogy, is the complexity of the human mind. I think it's really true that we are possibly the most complex system in the universe. Whether it's our brain, our heart, our mind, I do not know, but certainly we are a close proxy to the top of complexity. And I cannot help but thinking of an analogy between the complexity of the human mind, because to paint such a thing, it takes an enormous talent, but it takes suffering as well, right? Something that is deeply meshed into the complexity of the human condition. So I think there is serious work to be done along this line, and maybe, Peter, we can discuss how to develop further this idea. I still have time for history, not much, but okay, not much. I can only be jealous of David. No, you cannot compete with cosmology. It's just too beautiful, too fascinating. I did my best, but of course I cannot. All I want to say is that it is true that they are unique. They are kind of archaeology of the universe. The universe is just one, so they cannot repeat the experiment. And on Earth, we do much more mundane things, but up to a point, because this is called soft matter. Soft matter, as the name suggests, is the matter, our tissue, right? Is the state of matter which is most relevant to living creatures. And it's a mess, honestly. It's full of dirty details. But the cell itself, if you look into the structure of the cell, it's really a mess, like coming to Gianicolo through the Roman traffic somehow. But here is the typical ground where actually you really you cannot survive unless you know how to feed dirty details into universal principle. But there is, David mentioned this as well, there is unity in science and unity in knowledge, unity in culture. And this is not, the analogy here is just, analogies are good as long as they are no longer good. But there are very serious experiments where you take droplets, okay? Micro means 1/1,000,000 of a meter. And when you let them blow, and these droplets is a universe made of some 39 atoms, okay? And when you watch into the structure that they develop, and these are very, very cold, these are much colder than the universe you measured. It's basically 1 nanokelvin is 1/1,000,000th of a Kelvin degree. It's basically 0 to our perception. You see patterns which bear a resemblance with the patterns that you find in the universe. Don't quote me, of course, but there is some serious science, and I would like to, to me, the message is that science is one, knowledge is one, and as Pasteur was saying, and again I have to read myself, the role of infinitely small in nature is infinitely great. And I think that's, a nice statement which somehow puts together, humble softer matter and the beautiful and fantastic and mesmerizing science that David has been illustrating. And with that, I thank you so much for that.
Warm thanks to both of our speakers. We now have some time for questions. And while you may be gathering your thoughts, I'll ask the two of them if they have any immediate reactions to the other's presentation.
So let me begin by, in a sense, both a reaction and then sense a question, which is, some of this, when we look at complex systems, comes to what is our notion of beauty? And, there's this, perhaps on the largest scales and the smallest scales, I would say a very, basic sense of beauty is simplicity, beauty is something that's highly symmetric. And some of that's driven by what we can do mathematically. And, but if I look at the history of physics, often we hadn't had the right math to do the physics we needed, right? Newton has to invent calculus, right? Einstein didn't have to invent differential geometry, but he couldn't do the problem until he studied and learned differential. There was a whole branch of mathematics which he didn't know. And, when I look at, and I want to turn to, one of the areas that you've been a leader in, like, fluid dynamics, and you show this picture of this very complex structure. On the other hand, it has lots of regularities, right? And the energy on different scales, and one looks at what comes out in boundaries. You see fractals, you see lots of repeating patterns, and they're complex and rich. They're sometimes at the edge of what we have the mathematics to describe. So, and in the sense, it's for physicists, it's mathematics that describes our sense of beauty. And I wonder if it's, to put it as a question, what is failing when nature seems ugly? Is it our sense of beauty that's failing, that we're lacking the mathematics to appreciate the beauty of what's there? Or is it nature really being ugly?
Okay. Now you can, right? Thank you. Well, I wish I could answer, but I would say for sure, I totally agree that the sense of beauty, at least for us, is deeply rooted into the kind of math that we can develop. And as you know very well, David, the fractal geometry was a way of actually addressing the point I made. Yet, I think there is something subtler, and again, I would like to reconnect to the citation of Giorgio Nobel. I think we tend to perceive disorder as, a nasty thing, something which obscures our understanding. It is not like that. And I think the beauty comes from the correct blend of order and disorder. For instance, there are systems, now I don't want to be too technical, it's called stochastic resonance, one of the reasons why Giorgio got the Nobel. There are instances whereby just putting noise into a system, you can enhance the signal. So the noise works for you. And I promise, without noise, biology would not work at all. So whether we do not yet have the mathematics which capture this beauty or not, I think that's what nature does. And in that sense, I said, that's what I meant when I said, maybe nature likes ugliness, quote unquote, because I'm not sure this is really ugly, right? So to me, sweeping the ugliness under the carpet is a big mistake. But some details are ugly, some of them do not matter, and we do not have the right mathematics. How many times did we discuss about the landscape, right? Now we get, David has been so kind to me. Each time I go to New York, we have fantastic conversation, and so I'm very, very grateful to him. And I would like to make this statement publicly. I was delighted by how open he is. I went there with different problems than his mainstream, and he was immediately catching up and listening to me. So I'm very grateful. But just to say that there is development in science which is precisely targeted at identifying when a detail is relevant and when it is not. And we are not done at all with that, right? So I hope I did answer, at least in part.
Do we have some questions from the audience here?
I guess I have a related question, maybe about something that David was speaking about Einstein, like his perception of beauty when he was creating his analysis of the expansion of the galaxy and or the universe, and he couldn't perceive that expansion or didn't allow himself to acknowledge what he had maybe laid out as indicating the expansion? Because you described his perception of beauty failing in that moment to give him the conclusion that we now know is true. So I'm curious about that moment, and if now that we can understand the expansion, has our perception of beauty evolved from Einstein's perception of beauty, or is that still an ugliness that we've accepted that's against the aesthetic principles of mathematics?
Let me actually give two examples of Einstein's theory where he was led astray. One is the idea of a black hole. So when Karl Schwarzschild took Einstein's equations and he published it, and actually Schwarzschild was in the trenches fighting with the German army in the First World War. He was a German Jew who felt one's duty to Germany meant you had to fight for it. And at age 40, he was in the trenches, and where he would die. But before he did, he published a paper where he showed there was a solution that we today call the black hole solution. And Einstein looked at this and said, his mathematics are correct, but this is just so ugly, the universe can't allow black holes. Of course, one of the great triumphs of general relativity is the existence of black holes and how they merge and so on. So, Einstein was I think perhaps he certainly was one of the greatest physicists of all time, but even he was led astray when sometimes, you have a sense of what the universe should be, and even his mathematics guided him to something that violated his sense of how it ought to be. And did this with black holes, he did this with the notion of a universe that starts with, that's expanding. And today it is an open question. Did time begin with the Big Bang, or was there something before it? And we have lots of theoretical ideas on this. We struggled how we might make a measurement that would test this. It's one of the things done. But, at this point, people's mathematical models that they construct, or the new physics they construct, is guided mostly by their sense of do they like the idea that time has a beginning or not, right? Which is another piece of this, and something we don't know. And going to the future, one of the things that bothers me a lot about the universe is that it keeps expanding and getting colder, and will once be in the distant future be cold and empty. And it's not clear to me why I should care what the universe is like 100 billion years from now. But it bothers me.
If I could just jump in to both of you, I guess, mostly to David, I suppose. It sounds like somebody could listen to at least the discussion of beauty that's run through the two presentations and imagine writing, constructing a history of aesthetics as seen through the eyes of physicists. But once one does that, one then realizes that the physicists themselves lived in time and were educated to think about beauty through the canons of their own time. So I want to ask you a question. How do you think, the physicists you talk about, imagine beauty if they had their eyes educated through the art of the 20th century after the development of abstraction?
I think it's really interesting that abstraction arises the same time quantum mechanics does, which is, so Galileo and Newton, and actually, Einstein contributed to quantum mechanics. He hated this aspect of it. Classical physics is predictable, symmetric, smooth. Quantum physics is all about uncertainty. It sort of very much looks like, it's a pointillist view of the nature of matter, right? And I've found that it is in the same places in Europe at the same time that the ideas of quantum mechanics and the ideas of abstraction arise. And, I think one can quantum theory development is driven by some particular experiments. And in some ways, I thought, abstraction, I think, development of photography and things like that, there's lots of things that drive them at the same time. And, I think that when I think about, just and to go back to Sauro's point about complexity, if quantum mechanics and general relativity were the great ideas of the 20th century, so a lot of the great ideas of the 21st century may be ideas about our understanding of complexity and understanding what is the aesthetic there. And when I think of complexity, to me, it's also thinking about how do we think of, this is now putting on my hat as a foundation president supporting basic science, how do we bring theory as a way of thinking to fields like biology, in which it really is a very different culture than physics. And to me, when if symmetry has been the guide for physics, the concept of evolution is sort of the fundamental concept in biology, and it sort of shapes just the nature of things. Evolution selecting for things. And evolution is a very dynamical process in a very high-dimensional, complex space, yet it seems to be this sort of unifying theory. So 100 years from now, we're now 100 years past general relativity and quantum mechanics, we may have an understanding of complexity that's much, much richer. And with that, kind of an aesthetic, so maybe the question might be like, what is happening in our understanding, in the world of art, in the world of beauty? Have we had what are the fundamental shifts since the revolution with abstraction, which I think of as paralleling quantum mechanics? And will that give us, and physicists, or many of us, I certainly am one of them, think in pictures. And I think of what I do is I think of a picture, then I develop the mathematics to describe that picture. So having richer set of pictures enriches what we can do.
I have two hands in the room, and I guess questions from outer space. Let's take the questions from outer space first.
So I'm going to put two of these questions together. Nancy Turner would like to know whether Peter Miller's question could be inverted to ask, were artists also influenced by developments in physics during the 20th and 21st centuries? In relation to that, in talking about beauty and aesthetics, is the term symmetry being used in a Eurocentric way? Asymmetry is beautiful in other art cultures, and in both, however, there is balance. Is balance the way you both are seeing beauty?
I think when you look at the history of physics and mathematics, to view mathematics as Eurocentric is to deny the fact that many of the key ideas come out of the Islamic world, right? And it's sort of zero comes from India. A lot of things come from China, right? I have in my office a gift I got from my Festschrift, which traces my own intellectual history of my thesis advisor's thesis advisor, right? And it goes back to Damascus, right? So first, I think it's one's missing a piece of history in how we tell it, right? When we, it really is not, there's a point at which it's Newton sitting in London and Laplace in Paris, but that's not always where the action was. So I think, just on the history of math and physics is a much richer one than we sometimes know. I think this question of how does, and I think there's some interesting, I heard a lecture, it's about 25 years ago, so I'm trying to remember who did this, from our art history department at Princeton, talking about Galileo and how Galileo's discovery with the telescope is affecting art, and that lots of people went to see it, and a lot is showing up in paintings of the time, affected and influenced by what Einstein does. So I think it has been, that has been a two-way street historically.
So the idea of symmetry, the question was about it being Eurocentric, but whether in fact in what you have been discussing in terms of the messiness or the ugliness, that asymmetry can also be beautiful in other art cultures, and in both, rather than it talking about symmetry or asymmetry, beauty or ugliness, it's actually about balance. And that perhaps rather than using the term aesthetics, perhaps the term balance might be a way to describe what you are discussing.
Well, actually, I'm not sure I'm providing the correct answer, but to me, complexity is all about not being in balance, actually. It's always a matter of competition, right? But the competition has to be tight. Because if you win hands down, then the system is trivial. So now the question is, who are the competitors? I think it would be a little bit too simplistic to say symmetry versus broken symmetry is an expression that we use, which is super popular in physics. And we all know that nature likes symmetry, but it likes far better to break it, right? And the famous Higgs boson, I mean, that would take some math, but I promise it's a typical instance of symmetry breaking. And I think it was one writer, now I remember, said symmetry is the enemy of, I think consistency is the enemy of business and symmetry is the enemy of art. So I think art is knew long before scientists that symmetry cannot be beauty, but a complete disorder cannot be beautiful either. I think any system has its tight unbalance of the two. But in general, complex things happen when there are two competitors almost on a tie, and you are just waiting for the tie break. That's where complexity, and in my view, beauty, not in an aesthetical sense, but in an intellectual sense, that's where beauty thrives. That is my own view.
So we have time for two more questions. I'm going to ask each of the speakers
So it was George Bernard Shaw
to ask their question, and so we'll have both questions one after the other, and then we'll let the speakers reply.
Shall I go? I'm a molecular biologist, and I used to teach at Padova, so Galileo was a colleague. The most beautiful molecule in our body is DNA, and it obeys to the law of topology. That's why, and then fabricated enzymes that do topology for the DNA. Okay, that's it.
The stark separation between humanities and natural sciences is definitely characteristic of our time. It was definitely not the case in classical antiquity or the Italian Renaissance. I would argue it has a lot to do with how we organize production and consumption. You are at the forefront of academic research. Do you see this trend as something that will continue in the foreseeable future or not?
I worry that the pressures of funding, the pressures of goals of how we do things are pushing us to even more specialization, with not just this divide between humanities and science, but within scientific fields to subfields and sub-subfields and sub-subfields, and this I'm now in the unusual position of having gone from spending most of my time as an active scientist to being a funder of science, wondering what we can do in it. And I think, given the pressures that exist, most funding sources for people to deliver results immediately. And I think this has kind of produced the engineerization of science, really, and is so behind some of the lack of support for the humanities, certainly in the United States, is this sense of, well, what are you delivering to me for me tomorrow, right? As opposed to recognizing it's stepping back and getting the deeper understanding of things, that whether it's in the humanities or science, that in the end is the longer term value.
Thank you, Dave. If I may add, I totally agree. Actually, there is a very well-functioning agency in Europe. It's called the European Research Council, and it's really working very well. And they systematically encourage interdisciplinarity. But the fact remains that, as David pointed out, if you really try to present a proposal, and I did it actually myself, which is truly interdisciplinary, then you always end up in a crack. Many years ago, I applied for something between medical science and physics, and for the physicist, it was said, why don't you go to the medical doctors? And the medical doctors, why don't you go to the physicist? And you fall just in the crack. And so you have to, the only time where I managed to succeed was when I was really focusing super sharp on my mainstream, and then I got it. So I think that, yeah, the pressure for funding is not helping interdisciplinarity. There should be other, I mean, the RC is doing its best. I think David's foundation is, Simon's foundation is, it is for you guys to somehow break this trend to super specialization, but it's not easy. It's not easy.
And of course, that's a perfect setup to acknowledge where we are, which is an institution exactly designed for slow thinking and cross-thinking. Before we thank our speakers tonight, just to let you know that all of you are invited to an aperitivo upstairs, but not upstairs in the cortile as usual. But tonight, we take you through the garden to the back of the garden, where the aperitivo is set up on the site where Galileo did his observation in 1611, now occupied by a rather undistinguished late 19th century agricultural building. And with that, let us generously thank our two speakers for tonight.